Yeah, question one.
Question number 1 for homework 21.
Yes.
Okay. So what's your question while I open it up?
Let me finish it right now. Okay, so I set up the equations, but I'm not sure if they're correct. Specifically on part A.
Okay. So let's see. All right. So for problem 1 part A, you said you were having trouble?
Yes.
Okay, yeah. So for part A, what kind of adder are you dealing with?
Um, I believe it's a full adder.
Yeah, but it's not just one full adder, right? How many do you have?
No, yeah, it's wait, isn't a ripple carry adder two full adders?
A ripple carry adder is any number of adders greater than 1, and they're chained together. Yeah, so in this case, or in general, yeah, ripple carry adder is multiple adders. Not just 2, but it could be 2 or 3 or 4 or however many that you have. In this particular case, you have 64 full adders. And remember that for a ripple carry adder, the way that you essentially wire them together looks kind of like this. So that's a single full adder. And then if you want to chain multiple of them together, it looks something like this. And so what this is going to do is it's going to repeat until you get all 64 of your full adders together. And so this is a ripple carry adder. You essentially have your inputs for all of your bits that you're adding, exactly as you would imagine going to the inputs. And then you have the carry out of one full adder going into the carry in of the next. And that's why it's called a ripple carry adder, because the carry out from one ripples to the next, and it ripples down all the way down the line until you get to the very end. And so if you're trying to calculate the delay of this, all you need to know is the delay of one of your blocks, one of your full adders. So essentially, for your full adders, you're told that your delay is going to vary between, I think it was 150 to 450, yeah. 150 picoseconds to 450 picoseconds. And so the reason why this is important is because you want to find two things. You want to find the propagation delay, and you also want to find the contamination delay of your circuit. So those are the two things that we're asked to find. So if we want to know the contamination delay, remember that that's the shortest path through your circuit, and if we want to find the propagation, that's the longest path through your circuit. So looking at this image, can you tell me what the shortest path and the longest path would be?
The image on the right?
This entire thing. Because this is going to be a bunch of full adders. I'm not going to draw out 64 of them. You have the first one, you have full adder 0, full adder 1, 2 all the way to 62, and then 63 over there on the right side. So all of them there's a total of 64 full adders.
Well, isn't the shortest way like just straight across?
The shortest path is just what?
Like straight across.
So when you say straight across, you mean like this?
Yeah.
So it might help a little bit to look at the image that is given to you in the problem description, where you have a register on the top, that's your input, and then you have the output register down here. And these are feeding all of those signals. And they're also receiving all of the sum signals. So we're trying to find the shortest path from this register to this register. That's the path we're trying to find. So where do you think we could do that? Any ideas on what the shortest path would be? Just so you know, if you are talking, I can't hear you.
Yeah, can you hear me?
Yeah, I can hear you now. Oh, are you still talking? Because I can't hear you anymore. Oh, I think I heard that.
Okay, how about now?
I can hear you now, yeah. Alright, so how do you think we could find the shortest path?
Wouldn't it be like the S63 block? Like the block that's the most right?
This one over here? So when I specify a path, I need to know where it starts from and where it ends. So...
Oh, like it starts from A and B.
Yeah, so like it could start from A0 and go to sum 0, or start from A0, go through this full adder to C out, through that full adder, all the way to sum 36. Those are all possible paths, that kind of thing. So what do you think would be the shortest of those?
Well then, can it go to like A1? Start from A1?
Until where? And then where am I
until it will go. Okay, because so CN and then A1 and then it would go to S1 down.
Yeah, that's a pretty short path. Yeah. And in fact, I think I'll just go with S0 since it's the very first one. Sum bit 0, you just need to wait for A0, B0, and C0 to finish, or CN0, and S0 is going to be done and ready. So the delay of one single full adder, however long that delay is, that's going to be the shortest path, just one full adder, because that's all you really need to get through. That's the shortest one. So the contamination delay is equal to the delay of a full adder. In particular, the contamination delay of a full adder, just one of them. So in this case, we know that because it varies from 150 to 450 picoseconds, the shortest path will be 150 picoseconds. Does that sound all right?
Yeah.
don't think your audio is coming through anymore. Or at least I'm not getting it. Okay. Well, for the moment, since you're still muted, Good Noodle, I noticed you came in a little bit ago. Did you have any questions for me?
Is that for question one, right?
Yeah, that's right.
Okay. I just had a little question on the equation for the carry, like a head adder equation. We have the T and OR. So do I have to multiply? Do I have to? How do I get that? Do I just get it from the two input gate delay?
Okay, so which term were you trying to find?
The T and OR.
T and or. Oh, like the delay of an AND gate and the delay of an OR gate?
Yes.
Well, that's given to you in the problem description at the very top of problem 1. You're told that a 2-input gate delay is between 50 and 150 picoseconds.
So I just use that, and then I don't need to worry about like multiplying the entirety of those AND and OR gates, I suppose.
Well, all I'm saying is that this is just for one of those gates. So, you know, there's a few ways to go about it. You can kind of derive the formula for the delay yourself, like by hand, or you can use the one that she had in the slides. If you recall that one, it was the one that looked kind of like, I guess I'll draw it out. It's the one that looked like this. So if we are able to find all of those terms, we're pretty much set. So I guess my question to you is, which of these do you not know? Or which of those terms do you not know or have not calculated yet?
I don't know if my calculation is correct, but I think EPG is 150 picoseconds.
That seems pretty reasonable because that's just the delay of getting the propagate and generate signals. And to make each of those signals, it's just a single gate delay, which is 150 picoseconds at its maximum. So that sounds right, yeah.
And then for TPG block, in the video, she had 6 times whatever the PG, so I just did that same thing, right?
So not quite, because the blocks in this homework assignment are not 4-bit blocks, they're 8-bit blocks, so you have more gates.
Oh, I see.
So you'd have to figure out exactly how many gates it is that you have.
Wait for question 1.
Wait, for question 1, wasn't it a 64 and then an 8-bit?
64, a carry look ahead adder with
4-bit blocks. Never mind then, yeah. It's gonna be, it should be 6 gates.
Okay, so how do I find how many, how much I should multiply by?
So you'd probably want to draw out the schematic. So, like for your 4-bit blocks, if you looked in the slides, you would see something that looks kind of like this. So I'll go ahead and draw it out. And I think all the way to here. think it looks like that. And then each of these inputs, this is going to be G0, P, P1, G1, P2, G2, P3, G3. I think that's all of them. Yeah. Okay. So this is kind of similar to the schematic that you guys had in class. This should be identical to the one in the slides. And then, wait, is that right? 1, 2. No, that's right. Yeah, okay, cool. Yeah, that's right. So this here is going to be that big long chain of ands and ors. So in your case, it was 6. But for this one, the 8, for if you were doing it for multiple bit blocks, like for example, if we were doing an 8-bit block, like in this, instead of going G0, P1, G1, P2, all the way up to G3 at the end, you would go up to the highest that it goes for an 8-bit block, which is G7. So you'd have all these, and then you'd also have P4, G4, P5, G5, P6, G6, and then P7, G7. And so those would be all your input signals, and you'd keep chaining ands and ors together until you have all of those. And you just count up how many gates that is.
Okay, thank you.
Yep. And so yeah, in this example, it is going to be 6.
So I had a quick question.
Yeah, what's up?
For part A, since it's 150, would I have to multiply that by 64 since it's a 64-bit?
Good question, yeah. So like we discussed earlier, the contamination delay is just 150 picoseconds. So you're fine with that part, yeah?
Yeah.
Okay, and now you're talking about the propagation delay, correct?
Yeah.
So, I do agree we're supposed to multiply by 64 because the longest path is traveling through 64 full adders. But we're not going to multiply 64 times 150. Not the 150, but why do you think not the 150?
I'm not sure.
Well, what's the delay of a full adder?
Isn't that 450?
It's anywhere between 150 to 450. Why did we use 150 for the contamination delay calculation?
Because that was the 2 input gate delay for the shortest pathway.
No, it's not because it's a 4 input. It's not because it's the 2 input gate delay, because the delay we were calculating was from the input here at the input register going through a single full adder and then outputting to the sum bit. So it's not because it was a 2 gate delay, it was traveling through the full adder. That was the shortest path. But if you look up here, when you do the shortest path calculations, not only do you have to find the shortest path, you also have to figure out the shortest delay for each block within that path. So like we mentioned, a full adder can be anywhere from 150 to 450 picoseconds. However, the smallest delay possible for it is 150, because that's what they told us. So that's the number we use here. But for when we're doing propagation delay calculations, we want to find the longest path. So that means we take the longest to delay instead. So we would
so
do
it would then be 450 then.
Yeah.
For the longest delay.
Exactly. Yep.
Okay, gotcha. Okay, that makes sense.
All right. Okay, cool. And that was for the ripple carry adder. For the carry look ahead adder, it'll be a little bit different, but very similar. You guys have any other questions for me?
Yes.
What's up?
Continue off from the board. So I know that N is 64, K is 4, and so then the T and or, um, would that be the 150?
Yep, that's right. The longest delay of each 2-input gate, so 150. That's right.
Oh, okay, and then the rest are given. Okay, thank you.
Yep. That's right.
I was a little confused on the and or because I thought I had to like multiply it depending by how many or how many adders there were, but I think that's kind of what the n over k minus 1 is doing as well, right?
Yeah, that's what this term is doing essentially.
I see. Thank you.
You're welcome.
I have a question on the part B, part of 1.
Yeah,
Are
what's up?
we using the TCLA equation?
Could you repeat the very first part of your question?
Yeah, are we gonna use a TCLA equation? So the long equation where it's like propagation delay
You're
plus.
referring to this one?
I can't really see your board only because I
Oh,
think I have low internet.
yeah, it says
But-
TPG plus TPG block plus, and then a whole bunch of stuff. This is the equation for, I know it's a little hard to see, but it's the equation for the delay of a carry look-ahead adder, yeah.
Okay, yeah, that one. Then, yeah, do we use that equation to find the bulk propagation delay and contamination delays of part B?
You don't need it to find the contamination delay, but you would use it to find the propagation delay, yes.
Okay. So. Okay. Wait, so would it be 64 divided by 4 for...
For n over k? Yeah, I would.
Yes. Okay,
Yep.
got it.
Oh, I actually did make a mistake on one little part. This T and or term isn't the delay of an AND gate or an OR gate. It's not like the delay of one of them. It's the delay of both of them together. So if just a single gate is 150, then this is 2 times 150, or 300 picoseconds. So just keep that in mind. When I first read it, I thought it was for just one of those two, but it's for both at the same time.
Okay, so should be 64 over 4 minus 1 times 300 picoseconds?
Yeah, times 300.
Okay.
Yep. Yeah.
And you mentioned how for for part B of question 1 that the contamination delay you wouldn't need to use you wouldn't need to use that equation.
Yeah, you wouldn't need to use this because the contamination delay is still just one full adder delay. Because if you were to look at the I guess the pictures in your slides, each block consists of however many ripple carry adders are changed together for your particular block. So if you have a 4-bit block, it's 4 adders in one block, and you still have a path from the input A and B straight to the output some bit 0. So this path here, that path still exists in the carry look-ahead adder, and so that's still the shortest path. So it happens that the contamination delay for both the ripple carry and for the carry look-ahead adder are actually the same delay.
Thank you.
Yep. And and the last thing, the reason why they group together the and or term, they do that as one group instead of like individually, is because if you recall, in the picture that I drew, it was just a bunch of chains of and and or gates, and they come in pairs. So it's easier to just express them in pairs. That's the reason why. You don't have to do it that way, but that's why they did it that way. Any other questions for me?
Looking at number 2, it's only one question, right? So it's saying to use the equations we got from exercise 1, and then using the flip-flop characteristics, and we need to find hold time and setup time.
Yeah.
Or
Well, so you're asked to find the maximum possible operating frequency. However, in order to do that, and yeah, that's just one question. However, it's really two questions because it's asking it for the ripple carry adder and it's asking it for the carry look ahead adder. And then beyond that, in order to answer that question, you do have to calculate, like you mentioned, the hold time constraint as well as the setup time equation. So you're going to have to do both anyways. But at the end, all that they want like circled or highlighted is the answer of the maximum operation frequency for each of them.
Thank you.
Yep. And as you guys know, those are the same equations as you've done before. It's the TC, the clock time has to be bigger than the time coming out of the register plus the time through all the logic plus the setup time, and then the hold time has to be smaller than the shortest time out of the register and then the shortest time to propagate through the logic. So it's the same equations that you had before, and you don't have to worry about skew because there's no skew in this circuit, or at least you haven't been asked to deal with skew in this problem, so you don't have to worry about that. Another thing. Oh, yeah, go for it.
I had another question. Back to number 1.
Yep.
Part B. So, what would KTEA be?
What would what be?
Like, I know it's okay. For the equation that I see here is n over k minus 1.
Yeah.
And then multiply t and or, and then plus kt. That's what I have. I don't know if that's correct.
Yeah, KT. So you know what K is, right?
No, I actually don't.
So K is the same thing as what you mentioned earlier. Remember when you said N over K is 64 over 4 when you asked me that question earlier? It's the same K.
Okay.
So K is just what the bit size is of your block. And then the T there, that's the delay of your full adder. So you might want to label it TFA for the delay of for the time delay of your full adder instead of just T. But that's what that represents.
Got it. Okay. And then for this equation, we're solving for TPG. Right?
No, you're solving for TPD. I don't know if that's what you said.
TP. Well, how would we solve for TPD if it's not on the equation?
Well, this equation equals TPD. Because, so TPD, that's the delay of the logic between these two registers. So that's the total delay of everything, of the entire carry look ahead adder. And this equation is the delay of the entire carry look ahead adder. So this is all TPD. That's what we're trying to find. Just the result of this entire equation.
Okay. Got it. Okay. That's good.
Okay, actually, just to make sure I'm getting this right.
Yep.
So the K I have is 4, right?
Yeah.
And then I would multiply that by the longest way, which is 450.
Yeah, that's right.
Okay.
I know
And
it's a little hard
then
to see, but that's what I have here. Yeah, that's right.
oh, I can't see like you at all. Like I can't see the whole board or anything, but I'm trying to imagine it.
Okay.
But I'm thinking for the TPG block, would
Yep.
that just be 150?
Not quite. So remember when you looked at like pictures of the carry look head adder block that you had all the full adders and then you had like a bunch of chained together and or gates, ands and or gates, like one right after
Yes.
another. So the TPG block is essentially just the delay of that big chain. That's pretty much what that is. So if you were to figure out how many gates is in that chain, that's what you would do 150 times that. So in the case of your 4-bit blocks, I believe there were 6 gates. Like in the slides, you could see that there were 6 gates chained together. So it wouldn't be just 150 picoseconds. You have to go through all 6 gates. That's 6 times 150 picoseconds.
Wait, why is this 6 again? Is it because it's like
So you'd have to look at the actual schematic to see why it's 6. But the reason why is when you derive the equation for basically to calculate if you're going to have a what's it called? If you're going to generate a carry, the calculation for it is you do like G and P or G and P or G and P, and you do a bunch of those over and over and over until you get to the end of the block. And based off of how big your block is, the number of and or gates is going to change. So in the case of a 4-bit block, it happens that it's 6 gates. And if it was like a 8-bit block, I think it's 14, if I recall correctly.
Okay. Yeah, that makes sense. Now that I'm looking back at the slides, yeah, the slides make sense. Gotcha.
And, if you have like that picture right there in front of you, if you want to do like 8-bit or 16-bit blocks, all you would do is you would keep putting more P's and G's. So like on the right-hand side, you see like it starts with G0, and then it goes up P1, G0, P1, G1, and then it goes P2, G2, P3, G3, but it stops at G3. If you have more bits, you just continue until you end on G and then however many bits you have. So if it's 8 bits, you're going to end on G7. If it's 16 bits, you're going to end on G15. And you're just going to keep building up more and more of those AND gates together. Or more of those AND and OR gates together. You guys got any other questions for me?
I think I'm good. Thank you.
Yeah, for sure.
I have a quick question for problem 2.
Yeah, what's up?
So the figure 1 is just a representation. That's not. We don't need that per se, right?
Not really. I mean, all you really need to know is that the only thing between your two registers that you're using your clock for is just the adder. That's all you really need to know. Like, visually it helps to understand, like, when we draw this out, because this drawing is the same as the drawing given to you guys. It's just I've drawn each individual full adder, whereas that drawing shows it as a multi-bit full adder. Same drawing. The only thing it really helps you with is figuring out what, like, the contamination delays and propagation delays are. That's the reason why it's there. But you don't
I see.
necessarily need that in your, like, you don't necessarily need that picture to understand the problem or to do the problem.
So another question that I had was the very uh look ahead adder equation. You said that was TPD?
Well, in this case, yeah, because the only thing that's with it between our two registers, so like if you look at the drawing that was given to you right after part 2,
Yeah.
the only thing there is the carry look ahead adder, or the adder. And so in this case, the TPD of our circuit is the delay of the carry look ahead adder, or just the adder. So that's why TPD equals the delay of the adder. If there was extra circuitry in there, TPD would be equal to that plus the delay of that extra circuitry. But technically speaking, to be like precise, I wouldn't say TPD, I would say TCLA for the delay of the carry look ahead adder. That would be the like fully correct answer, or the fully correct way to write it, I guess.
Okay. Gotcha. Okay, sorry. Another question. So I calculated the CLA equation, and I got 7350 picoseconds, but I'm not sure that's correct.
77350, like 7,350.
Yeah.
That sounds right.
Okay.
Though I would probably just write it in nanoseconds if it's that big.
Okay, so I could put like 7.4 nanoseconds.
Yep. I mean, yeah, if you want to round to one significant or two significant digits, that's fine. I would just leave it at 7.35, but 7.4 works, yeah. You guys have any other questions for me?
When it says analyzing both hold time and setup time constraints, yeah, it's asking for me to first solve for T hold, and then I solve for TC, right? T sub C.
Yeah, you can technically do them in whatever order you want, but you should always do T hold first, because if T hold breaks, you don't then have to also calculate TC.
I see.
Okay. I know one of the students wasn't able to make it to today's office hours. They're going to be watching the recording, so I'm just going to go ahead and go through each of the terms and explain exactly what they are in the diagram. So TPG, that's the delay it takes to create every single propagate and generate signal. So, for example, if you take A0 and you take B0, and then you OR them together, that's the propagation signal of P0. And if you were to AND them together, you get the generate signal, G0. And this works for all of the bits, for A1, B1, A2, B2, all of them. To generate every single P and G in the entire system, it just takes exactly one gate delay, 150 picoseconds. And so that's why TPG here in this calculation is 150. In order to then take those P's and G's and propagate them through your block, you need to have them go through that big long chain of AND and ORs, the one that kind of ascends and they're all chained together. So like the one in the slides, it had 6 chained AND OR gates. So it's 6 times 150 to get through all of them. And then the output of that, so it'll look kind of like this. So all of these are all your P's and G's. So you're starting down here with G0 and P1, G1, all the way up to Gn minus 1, Pn minus 1. So however many bits you have in your full adder, those are the bits right before. And then the output of this goes into another 2 gates. You'd see this in the picture. It goes into the following. Where this here is the carry-in from the previous block, and then this is your propagate signal. It's just you and all of your propagates, because if you have a huge block, and you want to know if the entire block is going to propagate, that requires that each individual that requires that each individual column of your operation is going to propagate as well. So if you want your entire block to propagate, this column within the block has to propagate, and the one next to it, and all of the rest after until the end of the block, which is why you take all of the propagate signals within the block and you AND them. And I shouldn't put N, that should be K. The reason why it's K is because that's how many bits is in your block. And then if you have a carry-in and you're propagating, then that means the output of the OR gate is going to be high, so you're going to carry out, or if you generated it. So that's why it's going through an OR gate. And so where this term comes from, the TPG block, it's the delay of these two gates here. So we've accounted for the delay of all of those, but each block also has these two gate delays. And so each of these is going to, what's the word? Oh, sorry. That's not TPG block. That's the next term. So just to start from the beginning, TPG, that's the delay to get all the P's and G's at the very beginning. TPG block, which was what I was talking about, is the delay through all of these guys. So in the one on the slides, it was 6 gate delays, which is why here I put 6 times 150. And then the second part, which I got it mixed up with, these two gates here, after this is finished calculating, then these two gates can do their calculation. So you have to do the delay of an AND gate followed by an OR gate. That's the T and OR. But you can't just do it once like in all of these. Because here, TPG, all of the P's and G's for all of the blocks were calculated from the beginning, as well as the TPG block. Because all of these P's and G's are ready one gate delay after the clock hits. All of these gates for all of the blocks are done after this time delay. They don't depend on the previous block to do these calculations. However, this is the first time where it does depend on the previous block, because not only does this input of the OR gate depend on this, but it also depends on the AND gate output, which is dependent on two things. These propagate signals all ANDed together, which are done pretty quickly, but the thing that takes a long time is the carry-in from the previous block. So that is the dependence on a previous block. So these two gate delays don't all happen for all of the blocks at the same time. They finish for the first block first, and then you have to wait for the first block to send its carry-out signal to the second block, then the second block can finish doing this calculation. That's the reason why it's not just a single AND OR gate delay, because it's not that all of them are happening simultaneously. You have to wait for the previous block to finish and give you your current block the carry-in signal. So that's why you have this term multiplied out the front, because you're doing that a bunch of times. So for example, if you have a 32-bit full adder, and you have 4-bit blocks, that's 8 different blocks that you have that need to propagate. So you need to do 7 propagations. One from the 0th to the 1st, 1st to the 2nd, and then all the way down, and then the 6th to the 7th. The reason why it's only 7 and not 8 is because that last one doesn't have to propagate its carryout after. It doesn't have to do that because there's no other block for it to propagate to. So that's actually what you have here. N divided by K, and I was going to mention this earlier, that's the number of bits in your full adder divided by the bits per block. In that case, it's 32 divided by 4, which is 8. That's how many blocks you have. So N divided by K is also another way of saying the number of blocks in your system. And then you subtract 1 because the last block doesn't have to carry. So you take the delay of this, which is T and OR, and then you multiply it by the total number of blocks in your system minus 1. And so that's where this whole term comes from. And then finally, you have to then do your propagation for K number of, K number of bits per block. So in the very last block, you need to then have your full adders run their calculation. So in that last block, they get the carry in, and then they're able to run their execution in 4 full adder delays. So that's what this one is for. Here 4 because in that block there are 4 full adders. So one more time from the top, and then I'll ask if you guys have any questions before we end office hours. TPG, that's the delay of getting every single PNG. It's only one gate delay. And then TPG block, that's the delay for propagating through this big chain in each individual block. But all of those chains occur simultaneously, so you don't have to wait for like one block to finish for the next block to finish as well. The next term, though, that's the delay of these 2 gates right after this entire chain. And these are dependent on the chain as well as the output of the previous block. So these ones are chained together, and they depend on a previous one, so they don't all happen simultaneously. Which is why you don't just do one of them and they happen in parallel, but rather you do all of them except for the last block. So you have all your blocks. 32 divided by 4 is 8. That's all your blocks minus 1 because the last one doesn't have to propagate its signal. Time multiplied by the delay of these 2 gates. And then finally, when you do get to the last block, you need the carry in to go to the full adder input, and it's going to take, It's going to take however many full adders you have in that block times the delay of a full adder. That's the delay. And so that's the entire equation. And you don't have to know all that information to plug in, chug, and get the right answer, but it is important to understand kind of where the equation comes from. Okay, cool. So, did you guys have any questions for me before we end?
Yes, really quickly. So to get the frequency, it's 1 over the cycle time, right?
That's right, yeah.
Okay, so that would just if I have my cycle time, and then with picoseconds, it would just be the value times 10 to the negative 12.
Yeah, so like if it was 230 picoseconds. To get that into a frequency, you would do 1 divided by 230 picoseconds, which you said was 10 to the minus 12. So you can also rewrite that as 1 over 230 times 10 to the 12. And then you just calculate what's 1 divided by 230 and then write the answer out. It should be, in the case that I gave, it was like 4.2 gigahertz or something like that. For yours, I don't know what it's going to be, but it should be somewhere in the megahertz range is my guess.
Okay. Thank you.
Yep, no problem. Got any questions for me, Lou? Oh, I can't hear you. No. Oh, there we go. I heard that.
Hello?
There we go. Yeah, I can hear you now.
Sorry. No questions from me right now. It made sense when you went over it, like overview. But yeah.
Cool. All right. I think I'm going to go ahead and erase everything from the board. I'll give you guys like 30 seconds if you want to like look at it or take a picture or whatever, but I'll go ahead and erase it, and then after I'm done erasing, if you have any other questions, I'll answer them. Otherwise, we'll end office hours. Alright, cool. Here's this. Alright, you guys have any last questions for me?
I am good. Thank you very much.
Yeah, you're very welcome.
Have a great rest of your day.
You too.
Thank you.
Thank you, Victor.
Yeah, of course.
Bye.
See you guys.
Bye.